Okay, let's start. So today we will talk about the Little Computer 3. Little Computer LC3 is a simplified instruction set. So in this lecture, I will use LC3 to explain the basic operation happening in your computers. So the instruction set architecture is the hardware interface provided by your computer, which are programmer visible. For example, the memory organization. It includes memory space, how large your memory is. For example, 8 gigabyte. What's the minimum unit you can read and you can write? For example, maybe 2 kilobytes each time, or 4 kilobytes each time. And addressability, which means that the minimum unit you can index, how many bits per location. We also have a register set in the instruction set architecture. How many registers, what's the register size, and how they will be used in your application. Eventually, we have the instruction set, the opcode, data type, addressing mode. I will explain them in the following slide. So IRC provide all the information you need to do some assembly language programming. So the first important thing is the memory. For the LC3, the memory space is 2 to 16. Why? Because it's a 16-bit CPU. So the size of each address is a 16-bit, which means that you can index 2 to 16 locations. So this is only the maximum size of your memory. 2 to 16 is because this is a 16. So this is a K. This 1/10 indicates a K. And then we have a 6 here, which is 64. So totally, you will have 64K locations. If you want to insert DRAM in this computer, for example, assume that you have an LC3 type CPU. If you want to insert some DRAM in this CPU, you can do 32K. You can actually do any size of DRAM. Only the size of DRAM smaller than this size. Otherwise, the CPU will not support your DRAM size because it simply cannot index so large DRAM. So the addressability is a 16 bits because it's a 16-bit CPU. It has 8 registers, general purpose registers. Register is the memory component in the CPU, which can help you temporarily store some data. Generally, they are very fast. That's the reason why you have only a very limited number of registers. For the general purpose registers, there are only 8. So by 3 bits, we can index them from 00030 to 111, which is a 7, R7. So each one is a 16-bit. And again, you need 3 bits to index a register. Besides the general purpose register, you also have a program counter and some memory registers. These registers arithmetic operation or logic operation. So they can be only used for the special purpose register. The LC3 is very simple. It only supports 15 opcodes, including only 2 logical operations, and not. And the while is not. It doesn't even support multiplication. It has these many state movement instructions, including load and store, other types of load stores, and then the control instruction, jump, tab, branch, and some other tools to set or clear some condition codes based on the results, like NZP. I will explain them one by one in the following slides. It provides the support of 16-bit tools complement unit. So you can do only integer operation on this type of CPU. And it can addressing the memory by immediate type and register. And it can also index the memory, the PC relative in user based. So there are 3 types of arithmetic and logic operation. Only 1 arithmetic operation and 2 logic operation, and not. These instructions can only happen on registers. So we have only 8 registers, and they cannot happen on memory. Just the registers. If you want to compute some and or you have to load the data to the register first and then do the operation in the register. They can also support the immediate support, for example, 1 plus 1 or 1 value and 0. So you can actually set one of the operand as a constant. So I will show the data flow diagram with each instruction in the following slides. So this is the ALU or the data flow to complete a NOT operation. So this is the NOT instruction, and for the default most significant 4 bits are the opcode, which is 1001. So when the CPU sees this value, it will know that this is NOT. For NOT operation, you will have a destination register and software. Each of them is 3 bits because we only have 8 registers. And for all the other values here are ones, they are bits. So the function of this instruction is actually read the function in the software to the ALU, and then the ALU to the NOT operation, and write the result. So this is very simple. You only have a 2-step. Read the content from here to the NOT, and then write the result back. And these 2 registers can be the same. And then we have add and AND. Unlike the NOT operation, which has only 1 operand, these 2 have 2 operands, soft 1 and soft 2, and then it also has a different combination. So in the first step, they read 2 operands, soft 1 and soft 2. When the operands are ready here, they do addition or AND operation. Write the result at the end of this operation. So you can see that the only difference between these is the output. And these 2 instructions can also support immediate operation, which means that it will read the first operand from instruction language, and the second operation. So the second operand from the source 1. Then when the data are ready, both data are ready here to do the relation of AND operation. So this immediate data so you can see that the immediate data 5 bits from 0 to 4. So totally we are 5 bits. And then the result will be written back to the destination register. Again, the immediate data also have a sign, also can be something. In this case, there is a no source 2 register. So you can see the difference here. For this time, the least significant 3 bits is source 2. But these 3 bits are 0. Yes.
Is the immediate location in the instruction register, or is it the actual value?
The actual value. It's the actual value. For example, if you want to add 1 to this source 1, the component in the source 1, you just encode 1. So it's a constant. By reading this bit 5, you can, the CPU can understand whether it's an immediate instruction or a register-based instruction. So you can see in these 2 figures, the only difference is the bit 5. By bit 5, they can distinguish whether least significant several bit indicate an immediate value or a register. So this CPU is very simple, just one arithmetic integer operation and then 2 logic operations. So how to do the subtract? Yes, because it supports a 2's complement, you can directly add a negative number. How can we do the OP? Because it supports addition. So for example, if you want to compute A or B, you just add A and B. So how to copy some data from one register to another register? Yes, you can just add a 0. So how to initialize the register? And a 0. Any value and a 0 will be a 0. And then it can support these memory access instruction. For example, the load. Load means read some data from the memory to register. And you have different load operation. This is the PC relative base outside mode and the indirect mode. For the store, you have the same thing. And then we have the load effective. This instruction means you compute and then result will be saved. Then you read location. The location is actually stored in this way. You just get the result of that location. I will give you more examples. So the first one is a PC relative address mode. So the PC relative address mode aims to specify the address directly in the instruction. But unfortunately, each address and your instruction is also 16-bit. So you can see that from here to here, totally they are 16-bit. So even I use this, all the keys to indicate a address, I can do this 16-bit. If I want to indicate this is a load operation, then I have to use some bits, which means that I cannot use the rest within that. And the opcode is 4-bit. And I also need 3 bits for the register. So I only have 9 bits to index the graph. So these 9 bits is can represent the range like this. So 9 bits can help us to indicate 5 top numbers because we have a positive and negative. So this is the range, which can be represented by those 9 bits. And we can use this 9 bits to represent a signed offset. And then we can store the base in the PC. So in this way, the memory address can be something like this. The PC is 16-bit. So we can use the PC as a base and use this offset to visit the memory. By this situation, we can access all the address in this 16 bits. So this is the process of a load operation. The opcode of load operation is 0010. And then we have a destination register, which means that after you fetch the result, after you fetch the content from the memory, you need to store the content in this destination register. And then all the other 9 for the offset. So the process of this load operation is that I first read the value of to the ALU. And then I decode this offset 9 bits from 0 to 8 and sum them together. This can be a 2 complement value. So it can be a negative number. You can have a negative number is subtract. After you can compute this sum, you can write it into the memory address register. The memory address register will read the issue a read operation. For example, this location. This content is the address of this location. Then the result will be returned to the memory data register. And then you can store the data back to the destination register. Any question? Although the offset can be only 9 bits, we can use the PC to serve as a base to visit the memory. For the store, we have the same thing. The only difference is the operand. After we compute the memory location here, we read the data from the source to the memory data, and the issue is stored. We will store the data in this register to the memory location recorded in the memory. So this is the only difference. And then we will talk about the indirect addressing mode. With the PC relative mode, we can only address the data within 25 words of the instruction. So how about the other location in the memory space? The first solution is that the question is by this 90, we can only extract the memory location near this base location. How about the other part of the memory? How can we access those parts of the memory space? The answer, the first solution is that we first change this base. We first write the new base. Then we can do the PC relative addressing mode from there. In that way, we can access the so this is our first option for the indirect addressing. This is the flow. First, we read the data from the PC, and then the immediate data is in offset. We add them together. We use the sum and the memory location. We first read, then we read. And then future we can use in this location, we can use another result here. So in this way, we can access different parts of the space. So what's this so-called indirect memory access instruction? It's actually a pointer. We first compute pointer here. Secondly, read operation will read the content of the pointer. Again, this is a store. How to store some data to that pointer. We also need to compute the pointer first and then store the data to the location of the pointer. The third mode is as offset mode. The period method has a default. In this method, we have to read the memory twice. The memory latency is very long, so potentially this type of memory addressing mode is slow due to the extra memory access. So the base and offset addressing mode, potentially we can store the pointer in some register, some general purpose register. So in that way, we have a 4 bits for the output, 3 bits for call or destination, and 3 bits for the base. And the remaining 6 bits are zero. So instead of 9 signed offset, Here we only have a 6 bit, and we use 3 bit index to serve as the base register. So this is so-called LDR. It has a new opcode. It has 2 registers. One is the destination. You use this destination to store the final result back from memory. And then these 3 bits are for base register. We also have a 6 bit for the offset. So the process here is that we read this offset from here. Instead of PD, we read the other base. And then store the data, store the content in. This is the content we use. We will chase this content, read it. The rest of this memory location is the content language. And then the result will be returned to the memory data. And this data register will be stored final result to the destination register. So in this case, we only affect memory once. Compared to the previous one, it's faster. Yes.
How many locations?
How many location? What do you mean by location?
Right. So in this one, how many?
Because here you only have 6 bits. So for 6, you have a 226, which is a 64 location. It can be from minus 32 to positive 31. But you can change the value in base. So you can set the base to any part of this and then access the nearby or the neighboring 64 locations in this way.
In total, we can say that like because 3 part of base, so 32 minus 34, 31. If you get 64 to be
That's right.
64 times
That's right. That's right.
8, right?
That's right.
I think it's 9 locations, no? So what's the difference between LDR and
This base 16. This base is a 16 bit. So totally you don't have these many
okay.
base.
Okay.
So this is the base plus offset store instruction. It has a similar per step, but to do the write operation. At the last, we have the load effective address. In this instruction, we compute the address like the PC relative and store the result to the register. The address is actually stored in the record, not content. We will see the LEA, load effective address. We have a new opcode and a destination. The destination register is used to store the data effect from. Let me PC offset the number. first we read content of this to here, and then the input line is to here, and then sum them together. We directly use the sum to read the register. So this memory instruction is not used to fetch some data from the main memory. It can help you to write some value to the destination register. So there is no main memory access at all. This instruction is actually a like a arithmetic operation. It's just an addition here. You read some one operand from the PC. The other operand is encoded as a PC outside, and do an addition. You store the value to this destination register. There's no memory access at all. So this one can be used as the prior instruction of the base plus offset memory access instruction. Because in these instructions, you depend on this base. And the next instruction can help you to compute the base. So here are some examples. Again, on the CPU, now everything, no matter it's data or instruction or memory location, everything is 0 and 1. And then the instruction can be read like this. Totally, each instruction has 16 bits. And for the most significant 4 bits, these are the output. By looking at the output, you can know the type of the instructions. After you know the type of this instruction, you can further decode each part. For example, this is a 0101. For 0101, it's the AND operation. After you know this is an AND operation, you can further decode what's the destination register, what's the source one register, and what's the immediate file. So I will post a manual or specification of the instruction set on Canvas, and then you can do the decoding yourself here. Now we complete the arithmetic and the logical, and now we still have a control instruction. The control instruction is used to change the sequence of instructions. The first one is a conditional branch. The branch will be taken if some special condition is true. how to take a branch? You just add a signed offset to the PC to generate a new PC. So this is the jump offset. This distance you will jump. Otherwise, a branch will not be taken, which means that we just do the normal PC plus one. And the application will be sequentially routing. And we also have an unconditional branch. We just directly modify the PC. And the last one is the trap. Trap means you have some special, some IO device and some special which require the CPU to pay attention to. So typically the trap is implemented by OS services. Without check the PC to the graph of the OS function. After the OS handle this issue, OS will help you to return to switch back to your application. To change the PC again so that you can return to your own application. For example, if you run some application, you have a page fault. Page fault means the content, the data you are reading is not in the main memory, is not in the DRAM, it's in the disk maybe. So in this way, you need to tell the OS. There's a page fault, so the OS will do the page table replacement and install the data in the disk to the DRAM. After you have the data in the DRAM, after the OS take care of this issue, OS will notify your application to continue to run because the data is ready in the DRAM. So LC3 has a 3 conditional code register, NZP, negative, 0, positive. These 3 registers can be set by any type of instruction that write a value to a register. For example, add and not and load. So exactly only one of this 3 can be set. So if one is 1, the other 2 will be 0. And then we will talk about branch instruction. The branch specifies 1 or more condition codes. So if the set bit is specified, the branch will be taken. And we will use the PC relative address. The target address is made by adding some signed offset to the current PC. So this offset is actually the jump distance you will add on the current PC. So if the branch is not taken, then you need to sequentially run the code. So this is the branch instruction. The opcode is all zeros. And then we have a naive offset. the first step of this branch instruction is really PC, because potentially you need to modify this PC. Second, you need to evaluate these three registers. For example, if you write some if-else sentences, the if sentence will start one of these three registers. And then it will use this signal as a select signal for this mask. And the two inputs of this mask is the PC or the input of this mask is the the PC plus offset, the offset plus offset, or it's just one. One indicator, okay, I will sequentially run my code. PC plus the offset means whether you need to do this demo or run the code sequentially, totally decided by three vendors. For example, if your loop smaller than some iteration number, you do the loop body code. Otherwise, if you reach the maximum iteration number, you will do the jump. Any question about this branch instruction? So I will post the manual and some guidance on the LC3 instruction set on the canvas, so that you can read yourself. I will also post a simulator which implement this LC3 instruction set. So the simulator is a small computer. You can actually do some programming on that simulator. The simulator definitely support this branch and load, store, and all the addressing mode I talked about today. So if no question, we can stop. Thank you very much.